Welcome back. Here we have another optimization problem. This time we're talking about beam strength. The problem reads, a wooden beam has a rectangular cross-section of height h and a width w. The strength of the beam is directly proportional to the width and the square of the height. What are the dimensions of the strongest beam that can be cut from a round log of diameter 24 inches? And we're given a little hint there. Based off of that equation, the strength is proportional, so that's where the little k is coming in there, to the width and the square of the height. So S is equal to kWh squared, where k is just some constant of proportionality that depends on the type of wood. So we begin the problem by drawing a picture. So there's our log with diameter 24 inches, so I've drawn a radius in of 12 inches. And we're cutting a board out. So we're going to shave some off the top, some off the side, so that we have a rectangular board being taken out of the log. That'll have a height h and a width w. So that's our visual picture. And now we can again write our relationship down. S equals kWh squared. That's called our primary equation. But hold on though, as we look at that equation, you'll see that we have two variables. So we need to find some way to get that down to one variable. Well, if I draw the line from one end of the rectangle to the other, it would have to pass through the center of the circle, and therefore that would actually be the diameter. That's 24. And if you look at the picture now, you'll see that we have our good old familiar friend that we see in so many of these problems, a right triangle. So we can say that h squared plus w squared is equal to 24 squared. And then we can solve that for either h or w, but I'm going to solve for h squared. Because if you look in our equation, it's kWh squared. So I can just replace the h squared with 576 minus w squared. If you feel very adventurous, you may want to solve the equation for w. That's going to involve a square root. Plug that into the problem and work it out. You should end up with the same results, but this is far easier. So we substitute that in. We get S equals kW. And then h squared is now replaced with 576 minus w squared. And so we can simplify a little bit. And now we're just going to move over to the next page, rewriting our equation. And so now we have our equation written with one variable. So we take the, oh no we don't. Before you jump in and start taking the derivative, you have to remember that we need to find out what kind of restrictions do we have. Our equation is h squared equals 576 minus w squared. That's our auxiliary equation. We can get our restrictions from that. We know in order for us to have a board that both h and w have to be greater than 0. So we can say, okay, w is greater than 0, but there's going to be a limit to how big w could be because of this relationship. In fact, w can't be any bigger than 24. Once you get up to 24, then you're basically cutting the log in half and you don't have a board anymore. So we can say then that w has to be between 0 and 24 because both h and w have to be actual lengths. So now we can differentiate, now that we have our interval of restrictions. So we do that. We take the derivative of s. And we get 576k minus 3kw squared. Don't worry about the k. It's going to go away here in just a moment. So then we say, okay, when's our derivative 0 or undefined? Well, it's a polynomial, because remember, k is just some number. So it's never undefined, so when is it 0? And this is where I told you the k's, we can just divide k through both sides. And then we want to solve for w squared. So we bring the 3w squared over, 576 on the other side. Divide by 3. We'll get 192. Take the square root of 192. We get that W is 8 square roots of 3. So we know that W now is 8 square roots of 3. Well, once we know W, we can go back to our relationship to find H. H squared is 576 minus 8 square roots of 3. Simplify, we get that H squared is 384. H is 8 square roots of 6, which is about 19.6. If you need to at any time, please pause to catch up. W is roughly 13.9. So the dimensions we need to get the strongest beam will be roughly 19.6 by 13.9. But, as the purple bubble reminds us, are we even sure that this is in fact the maximum? And the answer is yes. How do we know that? Well, if we evaluate at the two endpoints at 0, it's 0. The strength of a 0 dimension board would be 0. And you would, again, not have a board if you made the width 24 inches, because you'd just be cutting the log in half, right down its diameter. So those both have a strength of 0. The point we found has a strength of 5320, roughly. So yes, it is a max. And now you might be wondering, well, what about that K? Does the K matter? No, it's just a constant. So the constant would just change. If it's at really 5320K, if K is 2, then it's going to be 10,000 or something. If K is 1.5, it's going to be something else, but it'll still be the strongest beam. The constant, again, depends on the type of wood you're dealing with. So that's it. Hopefully this helps you again with your optimization problems. The key is always to find. Too far. Your primary equation, and then we work to get that equation in terms of one variable. So again, our goal is to get that primary equation. Alright, good luck.